Hello, everyone. Welcome to another episode of Robo Papers. Super happy today to finally get Daniel Ho on the pod. So Daniel is the head of eval at 1X. He's got lots of things to say about world models today, I believe. So thank you so much for making the time, Daniel. Maybe as a start, if you can share a little bit about yourself before we dive in.
Yeah, absolutely. I've been at 1X for around 2 years now, doing a lot of work on policies, role models, evaluations. On the role model side, we've shared two, releases so far on how to use role models as policies, so they could take actions in the real world using our robot Neo, as well as on the eval side, how we can evaluate policies using the role model as kind of like a learned simulator. Yeah, prior to 1X, I also worked at Google. I worked on Waymo. I worked on some research there, and I did my undergrad at Berkeley.
Very cool. So and I think you guys just have a big drop a couple of days ago where you basically learn directly from world models to do something, right, with the Neo. So and then previously a couple of months back, you guys have another like blog post about the eval. So maybe it'd be great if you can talk us through the journey and what you can share about those.
Yeah, I think it makes sense to just dive right into the latest results and just see, what the current state is. I think it's very visual. I think when it comes to thinking about, what can role models do? So if we just were to go through, maybe just as a first topic, like what is different between a world model policy and another kind of robot policy, like a VLA policy. I think if you were to think about it, the main difference is that a world model is trained on video pre-training as kind of the main objective function that conveys, forward dynamics, if you will, to, in this case, predict the actions that the robot should take in order to solve a task. Whereas with the VLA, rather than learning directly on video or predicting what happens next in the video, you would instead regress what happens in the action sequence. So you would have a sequence of, data from, video frames and robot actions, and then you would predict, given that I see this current observation, this current robot image, I should take this trajectory of action. So it's kind of a more direct regression problem that VLA learns. And I think in this blog post, we kind of share that, there's a lot of advantages to learning in the world model way. The high level takeaway is that it really allows you to zero shot to new tasks because of the generalizability of video pre-training and of kind of the ability to do this kind of video next token, next frame prediction problem that kind of meshes very well with just reasoning through human video that has already been done a lot in the past. We can then transfer all of that knowledge into this policy, which now if you ask it to do a new task that even though we've never seen robot data of that task, we're able to understand that task because our robot has two hands, our robot kind of looks like a human, and we can extrapolate a little bit from what we've seen before. Yeah, I think if we were to go on to the next steps and say what kind of works today and what kind of tasks work, if we were to just look at some of the actual tasks that a robot policy can solve, there's some just direct grasping tasks where on the left side here it's the role model generation, on the right side here it's the actual rollout of that generation in the real world, which means that from the starting frame, which is whatever the robot sees, we'll first imagine what happens next in the scene if I were to grab the bag of chips. From that, I would get a sequence of actions that correspond to those video frames, and then I'll be able to execute. And that's what you see. And I think to us, it's actually very exciting to see how similar sometimes, these side-by-side comparisons can get, meaning that, there's something here in terms of if we can predict video correctly, then we can execute it. And that kind of cause and effect can become clear.
So the left side here is the generated video. The right side is the real rollout, and this is all zero shot. Just to be clear, very cool.
Yeah, you can imagine that, for example, some of these tasks might be a bit less zero shot, this kind of grabbing a salt shaker, or grabbing a bag of chips. But all of these new behaviors here are completely novel. There's nothing even remotely close to these kind of behaviors in the data set. We have never done wiping. We've never done this kind of badging into the office, for example. These are all just random things which we've tried to do. If you look at our data set, it's primarily a pick and place data set. So really the question is like, given a focus on pick and place, which is like, where you would start with from robot data, can we really analyze how well we can zero shot? So we're using the robot data primarily as a shim in order to, teach and post-train a model on robot morphology, robotic kinematics, like what are the constraints of the range of motion I have, for example, how far can I reach my hand out before it becomes unrealistic. Once I understand that, it doesn't really matter is what we're trying to convey, like what the type of robot data you train on is. All that matters is that, you have some data that corresponds to robot doing things that may or may not intersect with the actual actions you want to solve.
Sorry, Daniel. So just to be clear, right, on the left, so for the one model, when it's basically dreaming up this video, it's at prompt is presented with I imagine just one image and then with some text where the text will say, okay, pull up the chair. Is that what's happening? And then it will generate the video along with some action labels that go with those video.
Exactly. So you can imagine that the conditioning into the policy is like, if you hover over some of these bars on our plot, you can see that, for example, for steaming a shirt, the problem we have is right hand is holding the steamer, right hand brings the steamer up to the shirt, right hand steams the shirt in an up and down motion. And if we were to like find that, equivalent steaming behavior, it might be something like this, for example, that gets output through the video generation, and then the separate IDM process is what we use today in order to infer the actions that take you from one frame to the other, or the transitions between the frames.
Okay, so literally you in this, it's like this left-right scenario, you show the first image, and then that's what the one model imagine, and then on the right is basically you actually just apply the action label, the action instructions that's suggested by the one model, and then you apply it, and then this is what is actually being shown, and it's so close. Okay, got it.
Exactly. Yeah. So the action sequence, the prompt sequence, as you might have noticed, can be pretty long, right? Like, grab the bag of chips is like right hand picks up the bag of chips, left hand remains still. On sliding door, it could be really long. Like right hand reaches out and grasps the bottom of the metal handle on the right. Right hand slides the handle across to the left, closing the sliding glass door. So some of these prompts are like pretty specific, and because we won't exactly convey today, what exactly should happen in the scene. In the future, I think there's a lot of work to do to kind of just like work with both upsampled prompts like this, where we've really conveyed granular instruction, as well as just simple prompts like close the sliding door. And I think there's a kind of in the future probably going to be like some kind of interpretability layer between a VLM and some kind of maybe planner like this world model, where the VLM needs to output text into some manner that is interpretable and understandable by the world model to say, oh, I understand this kind of language.
Yeah. Maybe could you talk a little bit about, I think in your blog post you mentioned you guys start with basically internet scale video, and then you mid-train with some kind of egocentric, and then finally some kind of robot data. Maybe could you talk us through that? And I think somewhere in there you have some captioning that you do in addition to.
Yeah. So the process that I think we're sharing is that, from the web scale pre-training, we first mid-train on egocentric data, like say like 900 hours, for example, and then we'd fine tune on a smaller set of robot data. So say, for example, 70 hours. And again, like, this robot data may not be, the type of kind of action or task that corresponds to the ones we try out in the blog post. But the mid-training like may include like, just very general home style tasks that may, better correspond to some of these other chores. We didn't explicitly go out and, collect egocentric data of every single task that we've done. This is more or less just like unbiased egocentric data. And then if you look at, I think the kind of reason why we do this, we show, with some ablations, the ability of the model to improve from, being, for example, mid-trained on egocentric data. So here, like we show like between doing no egocentric mid-training and doing egocentric mid-training, we're able to like measure some delta in performance. First, we can measure this on video quality measured by human labelers who can label, does this video look realistic or not? Noticing like problems with physical plausibility or objects disappearing, or just like random artifacting, like if it looks bad, then reject it. If it looks good, accept it. We see that, for example, on generalization tasks, we see improvement when you add egocentric training. And interestingly, on in distribution tasks, we actually lose a bit of performance on the quality. We think that kind of makes sense because you can imagine that egocentric really is in order to diversify the task list. So you're actually trying to broaden the distribution. Maybe you dilute a little bit of the specific in distribution overfitting that you can have in order to generalize. And then in the real world, we also further run actual, ablation studies where we count the number of successes across each of these different ablations. And for egocentric, for example, you see that across most of the tasks, in this case, I think all of the tasks, there's like pretty significant improvement. There's like enough for us to be stat sig for some of these tasks. And for example, for scrubbing a dish, we found that egocentric was actually pretty important. So if you train on like scrubbing the dish with egocentric, you could really easily overfit to neo data without including that egocentric. So for example, like this is the same prompt, which is like very granular and saying like scrub the dish, and doing specifically that with the right hand, grab this point and scrub the dish. But the model may kind of overfit now to the robot data if all you see is pick and place, for example. But by including the mid-training stage, you are able to broaden the distribution like we hoped. And you can maybe see that, by the world model generations post mid-training stage are able to now, not overfit to grasping, but actually solve the task. And that was really good to see. So, pretty much all the failures on Scrub the Dish for, the prior like no ego baselines come from just a model not understanding the task correctly. So that was like a level of control that we got from Egocentric. And I think if you look at the other case you mentioned, the caption upsampling, that was also true too. So you could also look at the ablation results. You see like, caption upsampling seems like it generally helps. What that means is like, if you like think about language models or VLMs, now it's pretty common to train on not just like simple commands like open a door, but to be really granular, like second by second, to give a play by play of what's happening in the scene, and that's able to also exert a more granular level of control to the model.
Did you need to do anything like so for your egocentric data? Do you need to do anything like put a version of Neo's cameras on the glasses, or does anything work, or how do you think about that kind of stuff?
Yeah, that's a good question. For this experiment, we did not do any of that. So this is completely, like I said before, unbiased. Like not, we didn't do this egocentric data in our office. This was like kind of like more like egocentric data that you would kind of like acquire from third-party providers or you'd acquire from the web. Rather than it being like, we're gonna do egocentric data scrubbing in order to like target egocentric scrubbing. Like,
so you didn't even need to like specially collect it yourself. This is
correct. This is not collected by us. This is just collected by third parties where we didn't really provide an informed opinion about what they should be doing. So you can imagine it's like a lot of it is general home tasks or factory tasks or other places where people have collected egocentric data before.
Yeah, I'm actually curious, like whether you would know this. Like, I imagine if you like the very base, which is trained on so-called internet, like a video, right? Wouldn't there also be some egocentric video in the mix? What do you think this step of doing mid training, like egocentric, like just to highlight? I imagine there has to be some egocentric video also already.
Yeah. That's a good question. I think there definitely is a lot of that in the data mix. I think the problem is that it doesn't make up a big percentage of it. Like if you take an unbiased set of data from the internet, probably not a lot is egocentric and less of that is egocentric of doing useful tasks. So this is like a bridge, right? A bridge between the pre-training and the post-training where, we know in post-training time, it's going to be fully like first-person robot views, fully like, very specific home chores. So can we get to a middle point where we can train on, data, which is still of humans, which is still very in distribution, right? To the pre-training, seeing like egocentric data is, like you said before, not strange or like, kind of high perplexity to the model, but it is able to, understand that, it seems like we want to go down this egocentric way. I should focus on understanding these types of motions so that when we get to the robot style egocentric, it doesn't come as like a shock and overfit the model to that change.
Go
That's
back
at
to
least what we
the
think, right? So it's what we see from the ablations, but we're kind of also just speculating here to be clear.
got it. Do you mind going back to the success rate chart? We had the last one, the scrub.
This one.
Yeah, this one. So I'm curious what you think about the absolute success rate, especially for a scrub dish. So clearly, without an egocentric, it's basically useless.
Yeah.
Once you ego, then but it's also 20%, only. So
Yeah.
do you think it's just a matter of just really having a lot more egocentric? So hopefully you have more scrub, in these 900 hours? Or do you think it's still on the robot data side? Because you were saying the 70 hours is basically pick and place. Maybe you have to expand that as well. Like what's going to move the needle for this? Absolute?
Yeah, I think the kind of takeaway I have here is that the work here is still early and there's so many ways to do improvement from this. Like, given we didn't try very hard, to fit to the scrub dish task, you could, like you said, be more targeted and collect that. It wasn't the intention of the work to show results like that, right? Because at least the study here is like more like at a high level. Should we be thinking about world model backbones as a more scalable class of architecture than VLAs? So if we were to have gone and done that, that would be doing the VLA style of thinking, right? Rather than the world model style of thinking. And, of course we could fit results like that and make them, very close and collect, if you put a data engine to it, right? Hundreds or thousands of hours of that task. But it doesn't really convey the same kind of result where we're trying to see maybe the generalization performance because, we're imagining that even if we have a good sense of the task we want to solve in homes, the diversity in general is just going to be so different, right? The task of scrubbing a dish is going to be different because everybody has different dishes and different sponges and different homes, right? So it's a proxy to the general, transfer problem across tasks. If you were to look at the actual task itself, the scrub dish task is pretty hard, which is why I think the success rate as scored was pretty low. It's both grabbing the sponge and scrubbing at the same time. So we could find, it's like you have to grab the sponge and then have to scrub it, and I have to make contact with the dish, and that's actually kind of a pretty contact-rich task, right?
And you just have pick and place robot data too, so this is a pretty hard transfer problem, right? Is that fair?
Yeah.
Okay. Yeah.
But I think also to your point, another way that we're excited about hill climbing this performance that is enabled by having like a world model style backbone that wasn't possible before is the ability to do maybe like this post-training process that follows LLMs. For example, if we, rather than collect teleop data, like you would do in VLAs of this task, I could instead just roll this out, right? I get 20% success, so I don't succeed all the time, but I'm able to safely roll out these videos and try a bunch, get a bunch of failures, get a bunch of successes, and I could train on the autonomy data. The video sequences of those successes and failures could be used in world model training too, and then that would help me align the video model directly to these tasks and hill climb that 20% higher and higher, as well as allow me to do things like training value functions or, like we've seen in some other works, take the autonomy data and label it with actual more, information.
I think in your blog you also. Sorry, Chris.
You can. I was gonna ask how much of a difference you thought the pre-training data mix made. I guess because I could imagine a world where eventually you get just I don't know petabytes of egocentric data, and do you think you'd still need all that egocentric data, or is there still just stuff that's hard to capture from that, or what does the mix look like? Do you think you need do you have lots of kitchen tasks in it? I don't know. I
think being humanoid pilled, the answer is that we really want a recipe that learns very well from all human data, not only ego but exo, right? So the bet here is also that 900 hours of ego data is also, in the grand scheme of things, not a lot, right? It's also not enough to generalize for the most part. So we're really not only learning from the ego here, but we're learning a lot from exocentric, third-person view data of people doing things too. And that's really made possible because the morphology of a robot is very similar to the morphology of a human. I'd imagine transfer like this would become trickier. At least it would be less data efficient, right? If we're doing non-humanoid form factor robots. And there you see that, to your point, you may need to, do a lot more UMI style or other kinds of collection where you design specific kind of hardware in order to better fit the morphology of a custom robot, because my robot has wrist cams and 6-off hands that operate in this way with these kind of grippers. So I want to make sure that, I'm collecting like so-called egocentric data in that specific way. But it's more like, a more manual bridge than just directly learning from the web scale video that already exists of human doing.
Yeah, I just want to point out, like, as you guys were talking about, just, obviously this video is on loop. Like the one on the world model, I just want to point out two very interesting I just saw.
Yeah.
Maybe get Daniel and Chris thought on it. The
Yes.
first thing is that you notice when you drop it, it was on the first slot, and then magically it appeared on the second slot.
Yeah.
It started distracting me partway through too. Sorry.
Yeah, so it's doing some
Yeah, it's not
hallucination
perfect.
thing. But then at the same time, when you try to put the second, bread on it, it kind of know that there's something in there. It didn't drop straight away. So it's as if it understood memory, or like it has some spatial intelligence that it knows there's something in there. It won't drop all the way. Anyway, I just want to point out, like, it's at the same time it's silly, but at the same time it's also impressive.
Yeah, but also it got it right? Like the motions the robot did were correct because it actually works on the real side, right? So even though the bagel teleported a little bit, sorry.
Yeah, it takes like a little give. I think the bagel, like if you wiggle it, it just falls in, depending on whether it falls into one or the other. There's like a lot of high uncertainty, right? Like it's like a lot of the minor contact details would change where it falls in. And I think that's something which world models today don't have that precise level of control where you can say exactly like, I want to move you to like a couple millimeters forward so that you get into this one slot rather than the other. And that's, I think, something that we would appreciate training a lot more on robot data for, especially if the robot data includes things like tactile or higher, fidelity sensors that you could hill climb this more granular level of manipulation.
So do you think that this problem, so like the really granular differences in robot video generation, is something that will come out with scale, basically, that like I think it's not a huge issue and that with enough data it'll just be solved?
Yeah, I think that's like the simple way to look at it, right? Of course, under the hood, a lot of people had to do a lot of this, very hard things to make that work. Like, build really good robots with a lot of good sensors and build all the infra to make that happen. But those are kind of like known problems in a way, right? Things that we could hill climb, even though they are hard. And yeah, the idea would be that with this kind of policy, you can ask the robot to do things. It may fail, right? It may succeed. But that's going to, especially combined with the robot with high, dimensional sensing information, be able to hill climb the policy more and more. And if you really scale this up, right, like, if you deploy thousands of robots, then really quickly you'll collect, way more data than we've ever trained on. And that's the ability to, go from a world where post-training is like the cherry on top to a world where it's really a focus of, this kind of maybe more multimodal style post-training, where rather than just adapt it to the robot morphology, you're really adapting it to the full sensing suite of the robot that you have.
Yeah, that makes sense. So on the sensing suite note, I think one thing that I'm curious about, there's this old kind of style of world models, which is like state plus action in predicting a next state. That's not what you guys followed, right? You followed this kind of like, there's this sort of newer wave of these, which use like an inverse dynamics model to estimate the actions. And so how do you think about that? Why make that change, or what do you think what are the trade-offs?
Yeah, we could talk about the state action and next state one. I think that was what we used for evals. I think that's very clear and necessary for like making a true kind of model-based kind of simulator. But in this case, if the idea is that I want to be able to specify very open-ended actions, doing so in text space is more natural. This is more like the ChatGPT style of doing robotics. Right? Like we also built this very fun chat interface where we have everybody at the company try and just type to the model and have it do things. And people have tried really random things. We actually just show some of these videos from the random things people have tried. But it's like an interface, like ChatGPT for a robot. You connect to a robot, you see what the robot sees, pick up this thing, or open the door, and then you see the video. It's like, oh, good video, do it, or bad video, don't do it. And then it's like a very, very natural thing where people actually have a lot of interpretability into the process. I think if you talk about state action models, then if you can't really have this kind of like chatbot style, where like, how am I going to specify this trajectory in 3D space?
Maybe on this one, could you comment a little bit about how do you think the IDM part actually perform? Like, do you think it's more or less able to be faithfully, draw out the actual action that it seems to be suggested by the world model?
Yeah. Here we deliberately broke the IDM out separately. The IDM is actually the much more stable thing to train. You can imagine that the reason is because you could train the IDM on every single robot log you've collected, no matter if it's tele-up or autonomous, no matter if it's good or bad. The IDM basically says that from any starting frame, if you take any action, you get to any kind of next frame, or like another way to say it is given any 2 frames with any quality of action in between, you can just draw the bridge between those 2 frames. So, it's a really robust way of training that's really well specified, and it really is able to handle like everything. It's like converges very well. It's a classical supervised learning problem that has a very stable loss and very dense data you could train on. You could train on every pair of images, right, across a video, and you could take any pairwise combination. You could also slide a window across like any kind of sequence length. And there's no limit to it. Unlike more narrow ways of training like tele-op, where I must focus on this one specific action, and it has to be done exactly in this way to be correct and consistent. The IDM is more like we can trust the IDM. It's really about just generating the video. That's kind of what we found. In the future, we could also merge the two. In a machine learning sense, it seems very plausible.
How about in practice? Like I think in your blog post here, you mentioned something about like an actual inference. Like how long does it take to actually run the imagination? And then could you talk about that? And as things scales out, I mean, obviously this is your kind of first attempt.
Yeah.
Like how to do it in practice.
And that is a big reason to merge the IDM and the world model. That can make it faster, right? So then you don't need to run 2 models. You could just run 1 model. You could even run the model partially and do things like just care about the action part of it. The current model today takes between 10 to 20 seconds to run end to end. I think if you use the best hardware, I think it's like around 11 seconds to inference. So no, it predicts like 5 seconds of video. So it's like running synchronously, right? It's not running in the async mode. It's not like a closed loop rollout where you take actions continuously with the robot. I think if you could get the latency down, that becomes more and more feasible. And it could be more and more natural. But yeah, I think that's something where following the trends of like optimization work in diffusion models, like something that we're really want to show as a next step.
And how about also like maybe even allowing the world model to dream up like maybe more variations? Like, do you think that's helpful actually?
Yeah, that's a good question, and that's actually like sometimes in direct conflict to the latency, right, that you just mentioned. So we showed some work that you can generate multiple versions and pick the best one. And humans are very good at picking the best video from among a series of videos that look realistic. We actually have a very good like critic of videos, right, in our brains. So if you allow humans the ability to look at 8 videos rather than 1 video and just pick the best, then I think we saw a pretty good boost on most tasks, I would say, because you could like immediately rule out some of the bad generations, right? Maybe today, like the model still like needs to be kind of preference tuned or RLHF, right? It doesn't like always do exactly as you say. Maybe in the future this will go away, and there are 2 different ways to solve the problem. One is like you weed out the bad ones by generating multiple times. The other way is you train a preference function too, and you could be like, oh, given pairwise preferences across generations, I can just like post train the model on only predicting the ones that humans prefer. And that's also something I think that'll be really interesting next work.
And do you think this is the kind of thing that like also that you could just scale up? Like if you generated 64, you'd get even better. Like is this like a test time compute for robots, or I don't know?
Yeah, I think for some tasks, generations are pretty good all the time, right? Especially like grasping, right? Let's say we train on
So it's like-
grasping. Yeah. But if it's a really hard task, you kind of have to be more selective. So I think that's some interesting conclusions you can see where like, oh, some tasks do require a lot more thinking in order to get it right, which you could solve with test time compute. You could also solve with RLHF. At the planning stage, right, especially if you combine it with the value function, then you could really like automate this process and, spin on multiple servers and do things really in parallel. And it could probably be a combination of all of these, right? So if you really try like novel tasks, maybe it takes the model a long time because it's slower, and thinking through a lot of it, like in the LLM sense, but maybe it's able to do it, right? And that would be a new kind of avenue that you can explore with these kind of world model policies that wasn't possible.
Do you think it will take any clever methods or any changes to make sure that you get enough of a diversity of like options for that kind of thing to work?
Yeah.
Because like I could imagine it collapsing pretty easily to just a couple.
Yeah, with the fusion and the way we've done, our training, we saw like a good amount of diversity already. The collapsing mostly came from in distribution tasks, right? Where you could argue it's already good, you could argue it's overfit, right? Therefore, like, it's always doing the same thing. Whereas with rarer tasks, actually you see that the model is just naturally more uncertain. Because it hasn't really seen this before in your robot data set. It's like, oh, there's many ways to do it. Usually it doesn't collapse, but I guess that I think is future work to measure exactly how the trends line up there.
Daniel, how do you think about like, because right now you let it like basically dream up 5 seconds of like video and then do 5 seconds of action, something like that, right? I mean, in the real world, there will be tasks where maybe within the first 5 seconds, like 2 seconds in, something change.
Yeah.
So do you think this is just a matter of engineering you layer on into another system to make it more dynamic?
Yeah, I think that's a good question. There's many ways to solve this, and still like open research. I would say that in synchronous mode, you're always going to have this problem where you can't really handle dynamic tasks or changing environments. If you run it really asynchronously, right, where you're constantly kind of replanning and being aware of change, then you could solve it. There's also maybe ways to do system 1 plus system 2, right, that we've also seen where you can maybe have something more reactive.
Yeah, maybe this is a good segue to the other earlier paper where you do eval.
Yeah, absolutely.
Yeah, how do you know whether this world model version is better than the other one?
Yeah. Or just how do you even know a world model is better than a VLA?
Yeah.
Right? You could compare anything.
Yeah.
So I think maybe as a bridge, like, towards the point you mentioned earlier, like, a different way to formulate the world model problem, in the current work we're talking about, it was, going from image and text to, future video. But now we're going from image and action to future video. And the goal is to see how far you can do with action conditioned world models. So with action conditioned world models, you really want the world model to follow the actual command. So if I command the hand to move a certain way, I really, really need the model to predict video that shows that. If we could do that correctly, then this turns the kind of world model into a learned simulator where I can trust that, it's going to faithfully execute this action sequence and give me the future state of what would happen next, like a normal simulator. And therefore, you can do cool things with it, like do evaluations in it. I think people have also shown other demos. Like I think Tesla showed a demo of like, driving in this kind of world model too, where you could also maybe hypothetically put a VR headset on and do some actual teleoperation yourself in a world model. Those are all kind of possible if you can faithfully follow the action sequences. So what that kind of means is like from the initial frame, if you command different actions, that you can follow the kind of action sequence. So here it's like we commanded with 4 radically different action sequences, and the robot does 4 radically different things. It walks, it wipes, it does many kind of things. And if you're able to train it like that, then that the kind of evaluation work and future work kind of follows. The architecture here is so same as before. Let's say we have a pre-trained base model that understands video well. There's an extra step now you need to add to kind of turn the conditioning signal from text to actions, right? So actions is very robot specific and not something that you will normally see in kind of a base model. And normally, right, like if you see even egocentric data, like it's just the video itself. It doesn't really come with a direct action. And the action here is really the transition that you could take to go from one state to the next state. So how do the hands move over time? What is the kind of desired command to move the scene around? And it kind of mostly only applies to egocentric data, right? If you have, third person view data, there's less of a direct, like kind of, singular action that causes and affects the kind of scene to change. So it's kind of like a new concept that we're injecting. And so we can, kind of condition a model on actions with action encoder and passing the action latents into the model. And, if we train it right, then we can do that kind of conditioning. And for evaluation specifically, we also need to add this extra value piece on top. So not only do we need to predict the future video sequence, but we also need to predict some value or have a separate kind of value function that tells us, given that I'm, predicting this state or I'm in this state, how well have I completed the task? How much reward am I expected to get in the future starting from this state, or some discounted version of that. And if you can, predict a value, then you're putting everything together. You could take multiple different actions from the same state. Let's say each action was predicted by a different network. And then by passing it through the kind of world model, you're able to see different kind of values, right? Maybe with VLA number 1, you got a value of 0.3. With VLA number 2, you got a value of 0.5. And so you could say that, VLA number 2 performed better. That action sequence seemed like it was better, at least the world model judged it better. And then, from that point, now you could really, do things like, come up with complete analysis of like, across a whole aggregate of a data set, how well does VLA number 1 perform compared to VLA number 2. So if you look at some of these videos, you can see that we have action conditioned sequences where by replaying the actions of, say, a log, you're able to achieve very similar kind of generations of the robot state between the original and the world model generation. So the way the hands move look almost the same between the two, meaning that we're able to correctly get controllability of actions to be a property of this. And then now I think if you were to look at the next steps, it would be how well are you able to evaluate, how well are you able to simulate given the data you train this world model on. And the way that we measure that is on how accurate our alignment is. So you can assume that like if you have a real robot log where you've done a given task, I want to like grab an object, there's going to be a success or failure associated with that. I could have done that correctly, or I could have failed on that task. And then if you were to replay the sequence in the world model, you could also predict equivalent success or failure using your value function. And so if you have a score of 50-50, then you're pretty much guessing, right? It could be successful, it could be failure. I don't really know. And that's the kind of the baseline. If you get a score of 100, then it kind of means that, I can fully understand the world where I know and able to faithfully simulate, whether your action sequence led to a successful trajectory or not, and it will match your real log. The reality is it will be somewhere in between most of the time, because there will be some level of hallucinations, right? Some level of kind of just like hardness to simulate and some ambiguity that you'll never be perfect on it. But, having the ability to measure this kind of alignment means you could kind of tell how useful and how well trained this model was. The more aligned it is, the more kind of faithful it'll be, and, the less it kind of hallucinates. As you get to scores of like 60, 70%, if you imagine having a data set of, a couple hundred logs and you evaluate all of them, you can kind of smooth out the hallucinations, right? And if you look at the signal to noise ratio, it becomes enough that you're able to use it now for kind of measuring the performance across different tasks. That's kind of what we've seen. And if you look at some of the eval results, we kind of like show a couple of different things. We show checkpoint selection in robotics. Actually, it's pretty hard to know like when to stop training because the validation losses don't necessarily match the real world performance. Especially if you're training a behavior cloning algorithm, it would be nice to have a proxy estimate before we try every single checkpoint out in the real world. Or sometimes we're just lazy and we just only pick the last checkpoint, right? But that may not always be the best one. So here, like, you could evaluate all these checkpoints in the world model totally offline with computational methods. And then in the real world, we could do the same thing and measure the performance, and you kind of see which one performs better or worse. And we see in general, they correlate relatively well, where a better checkpoint would perform better both in the world model and in the real world.
Yeah, so you find this to be much more useful than or do you find this to be much more useful than a simulator, I guess? What do you think about this versus a traditional simulator? How about that?
I would say that they kind of serve different purposes. The area we're most excited about world model evals is, imagine that in deployment time, I run the model and I know the model is good on some tasks and bad on other tasks. And towards the longer tail, maybe it has certain failure modes that we know will always happen. You can use the world model to initialize the starting state of the world into any kind of state you want, right? It's kind of like a perfect real-to-sim setup where I can, always start simulating at any point. If I have a data set of like 1,000 real-world failures and they all are like, I didn't grasp the door handle correctly for this specific type of door handle. Then I could just create a data set of that and see, oh, now that I'm going to train on maybe on a different architecture or on a different data set to fix this problem, I can know, oh, did I specifically fix this door handle by targeting a data set on that during eval time? For simulation, I would say in the physics simulator or like a classical simulator, it's maybe better for getting really high throughput signal where it's really easy to measure, and not have to deal with hallucinations that just measure kind of the overall high throughput success rate, right? Like I could compare two checkpoints relatively and see, oh, is there on a high level like better kind of grasping behavior taken as a whole across VLA number 1 versus VLA number 2, whereas the world model lets you get granular and really specify exact failure modes. I think an example of this is like if you think about the Waymo case, right? Maybe you really want to be very specific about what the failure modes are. Like if you look overall at driving behavior, it's too broad of a category. So I only care about cases like, let's say, where there's construction zones, or maybe the stoplight's broken, or there's all of these various different features that are rare, and I could curate data sets of those encounters and replay exactly those ones. That's what you can kind of try to get.
Yeah, because I would have thought one of the big advantages would be like this part here where you're showing, where it's like a compliant soft object, right? It's always such a pain to get those to work in simulators.
Yeah. I think we saw like we're able to hold like a towel pretty accurately. Like if you want to like scrub,
scrubbing. Like I don't.
Yeah. I think there's some now that are better, but they're still pretty computationally expensive.
I actually have I don't know whether this is a philosophical question. So let's say like we have almost like a perfect world model where the value coming from this world model eval, like it's super good, right? It's really it's almost like 1-to-1 match to when you actually do it in reality. But even then, right, like I wonder, because ultimately someone need to ask the world model what to so-called simulate.
Yeah.
But in theory, what like the what to simulate part can be almost infinite. So you know what I'm saying? It's like let's say I ask a world model to test a VLA to fry an egg, but there are almost infinite way to fry an egg, especially for very long horizons. So it almost like okay, we have a perfect simulator called a world model, but then I can use it to simulate anything I want to very, very high fidelity to reality. But then what if I didn't manage to simulate some scenario that could have happened in the real world, edge cases in the real world? So that ends up being, in my view, could be actually the limitation is like, even if it were a perfect world model, what to use it to simulate on becomes the bottleneck. I don't know whether it makes sense. Yeah, because right now what you're doing, you're using action to prompt, right?
Right.
And then get a value. But my question is like, who is generating these actions? Like, what is valuable to run this computation to even like, I don't know whether what's
like if I put my evaluation hat on and try to like consider, how to solve this problem, we know at the long tail, right? We want the robot to do everything and anything, right? So like it's not capable of doing it today. We have no way of creating VLAs that could do completely open-ended tasks. So you can't, even put those actions in unless you craft them by hand, right? And if you take a step back from that, those evaluations actually aren't very useful, right? Because all our VLAs will fail on them, right? Everything gets 0% and it's boring, right? And it's like you're not able to discriminate between good and bad models. So the kind of sweet spot for these kind of models will kind of be a moving target depending on how the performance of state-of-the-art VLAs are, right? We want to kind of target it on tasks where, let's say, VLAs get 50% success, 50% failure. That gives us the most signal possible about which models are good and bad. And then as you graduate from those tasks, right? Like let's say you now manage to solve it by hill climbing on these metrics, right? We've seen in many other cases, like, now you're 99% on this task. It starts becoming boring again because every model is like 99%, right? And maybe the final percentage point gets hallucinated away. So it's like maybe not the perfect case in this scenario. So then I will need to build a new task, which again gets harder and harder. So I would say that the way you get there is like today, models can do, medium horizon tasks, maybe long horizon tasks of narrow nature, right? Like I think Pi has shown you can make coffee very kind of generally for that one domain task of making coffee. But you could like you said before, explain myriad tasks that you cannot do. So how do you like build up the VLAs using evals like this in order to put the rungs on the ladder to hill climb, right? So we know the top rung is going to be like full generalization. We could walk backwards a little bit in terms of like partial generalization, only generalization to home tasks in these certain kind of homes for these certain kind of tasks. Before that, you can be even more narrow, and then you kind of come back and walk backwards to today, where you're like, okay, I also walk forwards, right? I say that, today I can solve these category of tasks. I could also make tasks slightly more difficult and slightly even more difficult, right? Until eventually the two converge. And at that point, I think that would be the bull case for like, solving the long tail that you're talking about.
I see. How about like, okay, let's say if for this real world, world model eval, at what point would you say, okay, like, or do you think it will, or you always still want to still do the real world eval?
Yeah, I think the way I think about that is that you always have a limited budget for real world eval. So let's say on a given day, I could only evaluate 2 models very, very well, right? I could run thousands of attempts on each of these models, and I could get a very granular signal about which model is better, up to like 2 percentage points or 1 percentage point of difference in success rate across a couple of tasks. So if I can only evaluate 2 models, let's say my team is training like 50 models, 100 models a day, I need to pick which ones to do, right? I can't evaluate all of them. Like it could be random, like they could just like vibe check the model, or they could like, pick a random one and give it to me. Or, we could use a different kind of eval to rank the models first and hope there's some good correlation so that we pick the 2 best models every day to evaluate, right? So I think the real world budget is the most limited, and it's going to be the lowest throughput. And so we need some higher throughput signals to be able to, create the champion models that we go and evaluate every day.
Got it. But do you think there will come a day where this world model is just so good that you basically don't need real world eval? Or do you think?
I think if you think about deployment time, there could be cases where it could be more useful than real world eval, right? Because you could do world model eval on kind of the test set, right? You can like take cases where you've seen the robot fail in deployment time and evaluate in those cases. Whereas with real world evals, you're limited to your mock settings, right? In my office, I can try to mimic the test time result or test time environment, but it's only going to be a proxy to that. So with the world model, like there's only going to be 2 ways to like truly measure that test time performance, right? Either with world models where you initialize it from test time logs, or you run A/B testing in the real world on user homes, right? And that's a scarier prospect to do. Yeah, but you can imagine it's like similar to like, how Waymo or Tesla does it, right? Like before, I go and A/B test a new software on my car, I should be pretty sure. And I think a simulation for self-driving is actually more similar to the world model than to, let's say, our typical physics simulators. Because in self-driving, like, for Waymo specifically, like maybe they would only simulate the intermediate perception, meaning like they don't need to simulate physics. They don't need to simulate, any of the kind of high dimensional video information, but they could kind of initialize their simulation to already kind of test time states. So they could be like, oh, I have an interesting log of this car failing to do a certain kind of behavior in deployment time. And I could initialize my car simulation to that exact state where I could reposition all the cars in like as 3D bounding boxes, for example, into this original state, and I could run it there and get signal. So in that sense, I think the world model of robotics is the same as the simulator of self-driving car.
And you also have like Wave, who ostensibly trains in world models directly, right?
Absolutely.
Makes sense. I was curious. So you talked a lot about assessing VLAs in your world model, and we talked a lot about world models for planning. Have you assessed your world models in your world models? Seen how they stack up to the VLAs?
Yeah. I guess I'm worried that gets a little bit recursive, right? Yeah, maybe in some sense, like you would run into problems where you correlate
they're different
your
conditioning,
error.
right? They're different problems. Yeah.
Yeah, if you train like 2 independent models, I think that would be nice. I think that's going to be future work for us. But nothing stops you from doing that, right? Because the world model for eval treats just that you have a black box action creation mechanism that could be any kind of model.
Yeah, sounds like infinite like feedback loop that would just self-improve, and then we can just take the physics out of it ultimately.
I mean, I'm reminded of like the AlphaGo where they like when they were training it, they trained it against a bunch of old versions of itself, right? That was their world model, essentially, the opponent.
Yeah.
Right.
One kind of work we haven't talked about is like generating simulation data from world models, right? So you could also use a world model to generate synthetic data, right? So because you could generate video and you could also generate robot state, you could also use that to train world models and VLAs too. So it could really drive this feedback loop too, where rather than zero-shotting a task, you could generate, correct kind of rollouts of this task, and then train a VLA on that to teach a VLA how to do something too.
It's like everything is down to just compute ultimately, and
computing data.
Yeah, and then the video wins. Yeah.
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 Maybe like I guess we may be wrapping things up here. Maybe a final question from me, Daniel. Do you think it's a benefit like to have just one single embodiment that is in fact a humanoid, like kind of like Neo, for some of these to actually start working in the real, like the practical real world, so that my mom will actually get to see the product? Do you think it's actually beneficial this way, or do you think it's actually because the internet is full of like I don't know, even the egocentric, like different people are made differently? Okay, maybe like there are all kinds of different humanoids, right? Like do you get to the angle faster, you think, if you just have like one hardware that you are doing things with, especially you have the robot data part, right, which is all new?
Yeah. I mean, of course, I'm talking my book, right? Being part of 1X here.
Yeah.
I would say that like the bull case for the humanoids is that, number one, it's very scalable, and that, humanoids kind of by definition, right, of how we create it, can do any task because it could do what humans can do, or at least a very big portion of that. And then number two, the question is like, will it be faster to learn on a humanoid platform or faster to learn on a non-humanoid platform, like maybe a bimanual mobile manipulator platform? For humanoids, like I mentioned in kind of like, this podcast, you could really, really efficiently zero shot and learn from human data. That's the biggest advantage that we kind of lean into. And you get advantages of being able to more naturally tally up, more naturally control the robot, more naturally understand the data during training, both pre-training and post-training. And that could be a boost to like the speed at which you can deploy, right? Of course, maybe it's slower to collect the data, right? So there's these other trade-offs that you would see as advantages of other platforms. But we think that if it's possible for us to deploy humanoids today with a variety of tasks at reasonable, not great, but reasonable success rates, and it's possible for everybody to try this because it's a humanoid, right? So there's really no restriction into who can try it, especially if the humanoid is light and safe and compliant and all of these good things. Then that's a place where the humanoids will only get better, right? It's a platform which can scale by itself rather than outgrowing it at some point. You don't need to at some point, maybe another platform runs into maybe a scaling problem that humanoids wouldn't run into. And so because of that, it's easier to make a big investment and be like, we know this is both a short-term and long-term bet, right? So we can really do this for once and for all. And then it will only get better and better as we deploy.
Cool. Sounds to me. Yeah.
Chris, do you have any
it's been very really interesting discussion. Very cool work. So thanks for coming on.
Yeah, so super cool work. Especially that you guys have actual hardware to actually do real world eval on. Any like final things you want to say, Daniel? I mean, usually we round up with some like the usual question to ask. Maybe you want to answer this as well. It's like any cool papers that you've seen across that that
or demos cool or anything. I guess cool.
A shout out to.
Yeah, I think on the video model side, we are inspired by a lot of papers. I think we cite a lot of them, right? Like I think seeing the work that Vio and Sora maybe first and foremost are doing is kind of the existence proof that like there is a way for video models to get better and solve humanoid tasks, right? There's no reason that we can't, right? It could solve so many of these other really hard things. This is like not that hard compared to that. It's just a matter of the willpower to make that happen. And then if you look at other work, like in DreamGen, I think that's also been a big inspiration for us, and like UniPy with similar kind of techniques. And then I think if you look at maybe also some more modern works, I think like Mimic Video, for example, like show that maybe some routes you can use to speed up the kind of inference stack and make something that's also like really good for deployment time or inference time use. I think, there's a lot more work happening now in world models that we're excited about. And I think hopefully in the future, like, in a not too distant future, maybe in weeks or months, you can, come by an office and play with the robot and prompt it, and we give you like the chat GPT terminal of robotics, and you could just like be like, oh, do whatever you want.
Yeah, that'd be great. Very exciting. Cool.
Yeah, we absolutely are. Like, I think as you see, like it's so early, right? There's like so much work we could do to make the model better, and across the stack, right? I think on a world model side, the work is very clear. On evaluations, that's always, I think, going to be very important to have people who are very evaluation minded in robotics. But across, RL, across behavior cloning and VLAs and VLMs and high level planning and just overall mechanical engineering too, right? I think the nice thing is that 1X is vertically integrated. So I think we're hiring across literally every single kind of pillar of robotics.
So yeah, so if you're listening and looking for any kind of robotics job, reach out to Daniel, I guess.
Yeah, please reach out.
Yeah.
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 Yeah. Thanks, Michael. Thanks, Chris. It was really nice. And thanks for the invite.